So here we're going to be looking at the confidence interval. And what this confidence interval is going to let us do is compare the experimental mean and the experimental, well, pretty much the experimental mean to the population mean. Remember, the experimental mean is the average coming from a data set of a realistic number of data values, and the population mean would be the average coming from the entire population, an infinite number of data points. Okay, so the confidence interval. So it's not possible for us to calculate exactly what the population mean would be, because it's not possible for us to do an infinite number of data sets. But instead, it's going to give us a range. So this is the confidence interval, and what it tells us is a certain probability that we feel confident that the population mean lies between. Okay, so let's look at all these values, or these symbols. So this stands for the population mean. I'm going to write pop mean. This stands for the experimental mean, which we will have that value that comes from our data. Okay. N stands for the number of trials, the number of measurements. S stands for the standard deviation. And then T is a T value coming from a table. And we're going to look at that table here soon. And that value is pretty much, you're going to decide to what probability do you want to be sure of this population mean. So we can calculate, it's going to be a plus or minus, so like a number plus or minus a value. So again, it's going to give us a range that the population mean is going to be no greater than this and no smaller than that. So it's not possible for us to calculate exactly the value of the population mean based on our data, but using Gaussian distribution, this equation lets us solve for what the population mean range could be. So this is the table that we're going to be using both for confidence intervals and the t-test that we will talk about soon. This table is broken down by different confidence percentages. So the 95% is blue because that's the most commonly used percentage. The F-test uses 95% confidence. And so again, that's saying that if we're 95% confident, there's still a 5% chance that something went wrong with, that this didn't work out, that our calculation is telling us this is true, but there's a 5% chance that it's not. Okay, and on the first column over here, the degrees of freedom, remember that's the number of trials minus 1. Okay, so the way you would get which value of t to use in this equation, you would be told in the question what percent confidence you should approach the question from, and how many data values there were, data values minus 1, and you just go over and match them up. Okay, so as we go to the right, as we go to a higher confidence level, like confidence percent, the t values are getting larger. Now, if we look at that, it's going to make this number bigger, which means it's going to spread out our range, right? The plus or minus number on the back, it gets bigger. Well, if I want to be 99.9% sure that the population mean is within the range that I give you, then I'm going to say, all right, then it's between 0 and infinity. I'm just making that such a huge range that, of course, 99.9% chance that the real answer is going to fall within this range, because this range is pretty much everything. So the higher confidence you get, the bigger of a confidence interval, a bigger range you have. And it's just we're trying to make sure that really 99.9% chance. So that's why 95 is kind of where we stick with, because it's very confident. 95 is not 100, but it's up there. But the numbers aren't so crazy, I guess. So, for example, here's my 5 data values. The 6.375, 6.372, 6.374, 6.377, 6.375. So from those 5 data values, I've already calculated the average and the standard deviation. Okay. So what I want us to look at are what the population mean. Okay, so it's not possible for me to know exactly the population mean, but we could look at the confidence interval for the population mean. So at 90% confidence, I have 5 measurements, right? 1, 2, 3, 4, 5. That's how I know I have 5 measurements. The confidence interval for what we believe the confidence, 90% confidence of our population mean would fall within this range. So it's like they already did the math, okay, and it falls within here. Now, if I had done the same experiment, but I had done 21 measurements, and it happened to be that I had the same average and the same standard deviation. Remember on our t-table, the number of measurements plays a role in what the t-value is. So if I had done 21 measurements, the range of my population mean is smaller. The more measurements I do, the more confident we are about our range. So that's why as we go down on our t-table, the number of degrees of freedom, which increases the number of measurements, the values get smaller because we don't have to have as big of a range because we've done more experiments. We're getting closer to the infinity. We're never going to get to infinity, but 21 measurements is closer to infinity than 5, so I'm more confident in my values. So the more measurements you make, the more confident we're going to be. Okay, and obviously the standard deviation plays a role in this as well. Standard deviation is right there. So the smaller the standard deviation, the smaller the range, so the more confident we are in what our population mean is. So this is just showing data sets and showing with 50% confidence, these error bars are showing that plus and minus. And then here with 90% confidence. Do you see how huge the error bars are in the 90% confidence? Again, it's not because we actually know less than we did with 50% confidence. It's that we're reporting a number, or a range anyway, saying I'm 90% sure that the correct answer is going to fall within this range. So we made the range real big because we had to be 90% sure about it. And we only have a 50% confidence. We don't only be right 50%. Okay, so smaller error ranges with that. So let's do a confidence interval with some data values. Now these are the same data values we practiced with standard deviation. So the standard deviation value given here, if you go back to the standard deviation value or video, you can see where that number came from. Okay, so the confidence interval equation looks like this. Population mean is equal to the experimental mean plus or minus the value of the table from t times the standard deviation divided by the square root of n. Now I've already given you some of this. The unrounded average is x bar. Standard deviation is s. Okay. N is, 4 trials. So when I set this up, the average, and I should have really done the subscripts here, would look like that. The t value we're going to come back to in just a second. The s value is the 0.0004. And then the square root of n, the square root of 4. So what we need to do is go back and look at our table. And I'm going to also say we're going to be 95% confidence. So I'm going to go back to my table. So 95, it was 4 data values. So that means there are 3 degrees of freedom. So 3.182 would be my t value. And you're always going to have the table, 3.182. So this would be 3.182. So now I need to take 3.182 times 0.0004 divided by the square root of 4. And when I do that, the average is just, that number has not changed. Oops, except for I can't write. 925 plus or minus 0.0007027. Okay, so 1, 2, 3, 4, 1, 2, 3, 4. So technically the 027 be subscripts. So what I can do is just take this then and take 0.1002925 plus that value, 0.1002925 minus that value, and that will give me my range for what I believe to a 95% confidence. The population mean will be somewhere in this range. So it'll be no smaller than 0.099587 and no bigger than 0.100993. So we know that we're saying that with 95% confidence, the population mean is within that range. That's what our confidence interval gives us.